Hello, everybody. I am Andres, and I will be talking about what I learned this week in CS 4540 Intelligent Agents. So, I'll be talking about what a artificial neural network is, as well as talk about the universal approximation theorem, which is related to artificial neural networks, as well as talk about ReLU functions and how they are used as well in artificial neural networks. So, what is a neural network? A neural network is a method in artificial intelligence that teaches computers to process data in a way that is inspired by the human brain. So it consists of three main components: an input layer, which is, think of it as an array of values as input, and either one or more hidden layers. So here I have an example with one layer, and this one has two. And what and as well as an output layer. So what is actually going on here is that all of these different nodes are referred to as neurons, inspired by the human brain. And all of these neurons have, or it starts off here in the input layer with the initial inputs. So these initial inputs are in these nodes, and these nodes are connected to the following layer, which is the hidden layer. And all of these connections have weights to them. And the values of this hidden layer are all determined on the values of the previous layer, making it a feed forward network. And all of this can be represented by this formula. So in this diagram, you can see all of the inputs on the left denoted by x1 through xn, and all of them have a weight as well, and they're all converging onto one neuron. Because if you recall, or if you noticed, all neurons in one layer are connected to all the neurons in the previous and following layer. But anyways, this value, this calculation, is then pushed through a activation function, and it then has a bias added to it before it is moved on to the next layer. So, what is an activation function? Well, an activation function there are multiple kinds. This is one example of an activation function that's popular, the sigmoid squishification function. And what this function does is that it gets your value and it puts it between, or it spits out an output between 0 and 1. And this could be useful in a certain situation. There is also the ReLU activation function, which stands for rectified linear unit. It's a pretty simple function. It's just max 0 and the input. So as long as it's greater than 0, it uh, it makes this graph. And this leads into my next topic, the universal approximation theorem, which states that a feed-forward neural network with a single hidden layer can approximate any continuous function on a subset of inputs to any desired degree of accuracy, provided the activation function is non-constant, bounded, and continuous. But what does all that mean? Well, remember the ReLU activation function? Well, this could actually be used to represent any type of graph, for example. Here in this screenshot from Desmos, we have an orange line depicting a polynomial graph to the power of 3, it seems. And then we also have a bunch of ReLU functions. Uh, and the summation of all of these different functions pretty is pretty good at approximating this curve. And the more the more ReLUs that there are, or the more ReLU functions that there are, the more it'll fit this curve. And this is because, as we can look back on the universal approximation theorem, the network has to be feed forward, such as this one, and it can have just one hidden layer. So one hidden layer, and each of these functions are a neuron. You could think of it that way. And the 5 transforming the ReLU function, the +1, all of those little parameters are the weights and biases that we can tweak and alter to better fit the function. And yeah, so you could have any number of neurons to reach any desired degree of accuracy, and you can accurately predict a function as long as it's non-constant, bounded, and continuous. So non-constant meaning that it's not just a horizontal line, bounded, meaning that it's only between two specific values. Beyond that, it'll stray very far from the actual curve. So here you can see that the bounds that we're trying to replicate this function in are -1 and 4. And it must be continuous. So this function isn't piecewise, for example, or it doesn't have an asymptote in the middle. And yeah, that is why we can use ReLU functions to approximate any type of other type of function. And that's what we learned this week. Thank you for learning with me. Till next time, next week.